Alright guys, welcome back to Chem Talks. Today we are going to start our new unit on thermal chemistry. What we're going to be looking at in this unit is the effect of energy on matter and how the two interrelate with each other. So once again guys, please make sure you're taking good detailed notes. If you miss anything, pause the video, go back, rewind, make sure you get it. Okay, the first thing we're going to start talking about today is energy. We should start by defining what is energy. Energy is simply the ability to do work or produce heat. Think about when you get up in the morning, oh, I'm so tired, I don't have any energy. Well, that means you don't have the ability to do work. Okay, well, you got to get some energy. Well, that's what we're going to talk about in this unit is energy. Okay, energy falls under three main categories. The first one is potential, and this is the energy due to the position of an object. Where is it located? When we think about it in terms of physics, we think about how high is it above something. When we think about it in chemistry, we think about potential energy as the energy that is stored within bonds. Now, when those bonds between different elements break, it releases that energy into what we call kinetic energy. This is the energy of motion, the energy something has by moving around. The particles that make up matter, that they move around, they have energy. And then the third type is radiant energy, and we're not going to talk too much about this in this class, but radiant energy is energy that travels in the form of electromagnetic waves. Think about the electromagnetic spectrum. Everything from sound to color, X-rays, microwaves, gamma rays, all those are what radiant energy is. Now, with these three categories, there are six basic forms, or six different types of energy that we briefly want to mention. The first one is chemical, and that's what we're going to spend a lot of our time talking about. We also have nuclear, that's the energy associated with the nucleus of an atom. We think of nuclear power plants or nuclear bomb releasing all that energy. We also have electrical energy, which we use every day when we turn on our electronics, turn on lights, make our car go, right? We have electrical energy flowing through all that, the movement of electrons. There's radiant energy we talked about, which is electromagnetic waves, mechanical energy, energy of movement, and then thermal energy, energy of heat. Okay. The neat thing about all these forms of energy is that they're just various forms of energy, and one form can easily be changed into another form. And that's very important because what we find out is that this energy is never lost. It simply changes from one form to another, and that's what we call the law of conservation of mass. You've probably heard of this before. Law of conservation of mass states that energy cannot be created or destroyed. It can only change from one form to another. So potential changes to kinetic, chemical changes to thermal energy. Okay, and when we see these during these different changes, energy lost by one object must be gained by another object. So technically the energy is never lost. It's just changed from one form to another, or maybe from one form to several forms. Now when we look at these as energy being given up or gained, we can talk about two types of kind of reactions. First one is exothermic. Exothermic refers to a reaction in which energy is given off. Probably the easiest thing to think of this are those, if you ski or go hunting, you get those little hand warmers. You crack open the package, it exposes the chemicals inside to air, they react with each other, and heat is given off. We keep them in our gloves or boots. Okay, so that's an exothermic. The other type then is endothermic. This refers to a reaction that absorbs energy, or heat energy must be put in. Okay, this is like those ice packs. If you sprain an ankle or something, or a knee, you take one of those chemical ice packs, smack them together, it breaks a little packet inside, which combines a dry chemical in there with water. Starts the reaction. The water then starts absorbing heat from its surrounding. It's taking heat out of the surrounding, and it becomes cold. We get these chemical ice packs. So exothermic is a reaction that gives off energy. Think about exiting, right? The energy exit off, where endothermic refers to a reaction that absorbs or takes in energy. Now, we can measure energy, and we use slightly different terms depending on what perspective we're talking about. Probably the one that you're most familiar with is the calorie. Okay, the calorie can be defined as the amount of energy required to raise 1 gram of water by 1 degree Celsius. Remember, 1 gram of water is equal to 1 milliliter, so a very small amount of water. How much does it take to raise that by 1 degree Celsius? Now, for practical purposes, this is not a very useful term. It's really small, okay, and it would take lot of calories to do anything significant. So we've come up with the term kcal, or big calorie, big C calorie. Please notice a capital C versus a lower c. And a big C calorie is the amount of energy that required to raise 1,000 grams of water by 1 degree Celsius. So it's a much bigger quantity. This is the energy unit that you see on food packaging when you read that your chips have 250 calories per serving. Well, they're talking these kcals, or these big C. Please do not get these two mixed up. Understand that 1 big C, or 1 kcal, is equal to 1,000 calories. When you write them, make sure I know that it is a big C, not a little c. Make them very distinct from one another. Now in chemistry, we go with the SI, the System International Units, and the calorie is not the base unit for that. For SI unit, the modified metric system, we use what's called the joule. Okay, the joule is a SI unit of energy, and what we find is that 1 calorie is equal to 4.184 joules. So this is a conversion you'll need to know. In fact, you'll need to know both of these. That 1 big C, 1 kcal, is equal to 1,000 calories, and 1 little cal is equal to 4.184 joules. Because like I said, in chemistry, we're going to use more of the joules than we will calories. In biology, we have a tendency to use calories rather than joules. So make sure you get these down. And you do need to have these memorized because you will be held responsible for them. Okay, let's try a practice problem here. Simply converting. Okay, we're going to convert 150 calories, big calories, to little calories. And the way we're going to do this is factor labeling. So with any factor labeling problem, as we did earlier in the year, we start with our ping pong table. Okay, and we start with what we're given. We're given 150 big calories, and I know that 1 big calorie is equal to 1,000 little calories. Once I have this set up, my calories cancel out, my big C calories, and I'm left with little c. So now all I do is take 150 times 1,000 and I end up with 150,000 calories. Pretty simple. The big key is make sure start with what you're given, then what you want to get rid of goes on the bottom, what you want to keep goes on top. Make sure you're copying these practice problems down so you'll have them in class when we do some problems on these. Okay, let's try one more. Let's convert 75 big C calories, kcals, to joules. Now, if you look at our conversions, there's no direct conversion between big C's to joules. So what we have to do then is to go from big C's, kcals, to little c calories, to joules. So set up our ping pong table. Start with what we know. We know we have 75 big C calories. Well, just like before, we know that 1 big C calories equals 1,000 little c calories. Now our calories cancel out. Now we got to go from calories, little c calories, to joules. Well, we know that 1 calorie is equal to 4.184 joules. Our calories cancel out. Now all we have to do is take 75 times 100 times 4.184, and we end up with 313,800 joules. Pretty simple. Now the other thing we could do, we see sometimes, a lot of times, since this is a pretty big number, we can convert this to what we call kilojoules. Remember, a kilo is just 1,000, so if we do 1,000 joules is equal to 1 kilojoule. So sometimes you'll see that conversion as well, so be aware of that. All right, let's look at heat and temperature. Heat is a quantity of energy. Okay, it's a form of energy. Okay, it's calculated from its effect of temperature on a given quantity of a substance. So it depends on how much of something we have. As we just talked about, we measure it in either joules in chemistry, or we can do it in calories. And it's also known as heat energy. We abbreviated the letter Q. Okay, so heat or heat energy are the same thing. Temperature then is a degree of hotness or coldness something is. Okay, it's measured on a thermometer in a specific scale. We can talk about Celsius, we can talk about Kelvin, we talk about Fahrenheit. So temperature is really how heat affects an object. Okay, the effect of heat energy on the substance. Let's take a look at this. Let's say we start off with 1 unit of heat. Let's say we have 100 joules of heat. We're going to put in each of these different containers. We have a 25 millimeter container, 50 millimeter, 75, and 100 milliliter. And these contain water. Okay, and what we see is that even though we're putting the same amount of heat in, 100 calories or 100 joules, the effect on this is going to be different. For maybe in this first one, what we see, it raises the temperature to 100 degrees. The same amount of heat, If we double the volume, it may be 50. If we make it 3 times as much, it's 25 degrees Celsius, and we make it 4 times as much, it's 12 degrees Celsius. So what we're doing, even though it's the same amount of energy, it's just dispersing that energy over a greater area, so it has a less effect. So temperature is a result of heat's effect on an object and kind of the quantity of that object. So let's talk about temperature. Okay, a little history of it. The first device made to measure temperature was done by Galileo, and he invented the first temperature device. Maybe you've seen these Galilean thermometers here. These different little bulbs will raise or lower depending on the temperature, and I believe you read it from the top. Okay, so this was way back in late 1500s, early 1600s. The first reliable scale was done by Daniel Gabriel Fahrenheit, who gave us the Fahrenheit scale. And why did we use the Fahrenheit scale? Well, he was making thermometers, and he created this arbitrary temperature scale. And the reason we went with his is he was making the best thermometer at the time. They were the most reliable. And he based it on the human body temperature of 100 degrees. The story goes that he had a little fever when he did it, because we know human body temperature is 98.6. So it was originally based off of the 100-degree human body temperature. But that's all it was based on. It was kind of an arbitrary where the points fell. Okay. Later on came Andre Celsius, and Celsius gave us the Celsius scale. And basically, his scale was compatible with the metric system, and he based it on the freezing and boiling points of water. We know water freezes at 0 degrees Celsius and boils at 100. So we could break that up in tens once again. So his was actually based on something. And the third scale that we have that we will talk about was given by William Thomson, who is known as Lord Kelvin, and gave us the Kelvin scale. Okay, and this is the SI unit of temperature, the Kelvin, not Celsius. Don't confuse that. The SI unit is Kelvin, just like the energy unit was joules. Okay. The nice thing about the Kelvin scale is that each degree in the Kelvin scale is the same as the Celsius. So if we change 1 degree Celsius, we've changed 1 Kelvin degree. If we change 1 degree Celsius, we change more than 1 degree Fahrenheit. Okay, so Celsius and Fahrenheit don't line up nicely, but Kelvin and Celsius do. Okay, so 1 Kelvin equals 1 degree Celsius. Please note there's no degree sign in Kelvin. It's just 1 Kelvin. The other thing about the Kelvin scale is it can never go into negative. It is always positive. Well, to do that, we have to figure out what could be the lowest temperature that exists, and that's what we call absolute zero. Okay, it's 0 kelvins. It's the lowest possible temperature. Okay, equal to minus 273 degrees Celsius. So what's important about absolute zero is that at this point, when we reach it, we believe that all molecular motion stops. Now, it's never been reached yet. We're really, really close. Our scientists are really, really close. Actually, CU in Boulder is one of the leading researchers on this, so they were. But we haven't quite got down there yet. But they believe that once we hit 0 kelvins, that all molecular motion stops. So that's the lowest temperature. So the Kelvin scale is based on absolute zero. That way there's no negative numbers. This comes into play later when we talk about gas laws, because if we do gas laws with negative numbers, all things get messed up. So understand 1 degree Celsius is equal to 1 Kelvin degree. Okay. Kelvin scale is based on absolute zero. Celsius scale is based on the freezing and boiling point of water. Now let's talk about how we convert from Fahrenheit to Celsius, okay, and vice versa. Here is the equation. It's 5/9 times whatever the Fahrenheit degree temperature is minus 32. Okay, doing Celsius to Fahrenheit, it's 9/5 multiplied by the Celsius degree plus 32. You're going to need to memorize these, okay? You're not going to have these on the test. You're going to have to know these. In class, I'm going to show you a graph. We're going to create a graph, or a diagram, I should say, to help you memorize these and understand where these numbers come from. So you can either, I would copy these down now, but you can either memorize these or the chart that I'm going to show you. Remember, you're going to use my calculator test, so you're not going to be having your fancy TIs which do this for you automatically. So you're going to need to know one way or the other. So get these down. Now, let's do an example problem. convert from 100 degrees Fahrenheit to Celsius. Well, 5/9 times 100 minus 32, okay, equals 37.78 degrees Celsius. Okay, let's try going the other way. What if we have 100 degrees Celsius to Fahrenheit? Well, we take 9/5 times 100 and add 32, so we get 212 degrees Fahrenheit, which makes sense, right? This is the boiling point of water in Fahrenheit. This is the boiling point of water in Celsius. Okay, what about our last one, our Celsius to Kelvin and vice versa? Well, like we said, a degree in Celsius is equal to 1 unit change in Kelvin, which makes it really nice and easy. Okay, so to figure out Celsius from Kelvin, you take your Kelvin minus 273. Okay, if you're given Celsius and want to go to Kelvin, you add 273. And just like the other ones, yes, you need to memorize this, so please copy this down. Let's try an example problem here. Okay, convert 100 degrees, I should say Celsius, to Kelvin. Okay, so 100 degrees C plus 273 equals 373 degrees Kelvin. Really simple. Celsius to Kelvin, add 100. If we're going the other way, if we have 100 kelvins to Celsius, we subtract 273. So 100 kelvins minus 273 equals negative 173 degrees Celsius. Pretty simple, but you do need to know how to do all these conversions. Like I said, in class, I'll work you through a diagram on how to remember the Fahrenheit to Celsius a little bit easier. Okay, thanks for paying attention today. We talked about energy, the different categories of it, different forms of it. We talked about how energy can change from one form to the other without it being lost based on the law of conservation of energy. We talked about ways to measure energy in either the little c calorie or the big C calorie. We also talked about, in chemistry, we use the SI unit, which is the joule, and 1 calorie is equal to 4.184 joules, and how to convert back and forth between those. And then we talked about our 3 temperature scales, Fahrenheit, Celsius, and Kelvin. So make sure you know how to convert between all those temperature scales, and we'll see you in class where I'll show you a diagram on how to remember this a little better. We'll actually explain where we derive those equations from. Until next time, guys, come see me if you have any questions, and take care.